I'm going to be talking about, I guess, mechanical system design, but largely in the context of the buildings you're seeing in these photographs, larger MERB buildings. At RDH, we're working on about 5 million square feet of large building passive house at the moment, including a 750-bed student residence out west and now an 800 student resident project in Toronto. So my agenda, yeah, we're going to be talking about multi-unit residential buildings, the heating and cooling systems, challenges around trying to find anything even close to right-sized. Challenges with humid climates. We are in a humid climate, especially here in Southern Ontario. Potential solutions and some things that are happening in the future. If you're paying attention to what's going on in the heat pump industry, things are changing mightily fast. We have boiler manufacturers now getting into heat pumps. Lars is going to make a heat pump. So things are getting interesting. Passive house is all about the enclosure until the building gets bigger. I think one of the dirty secrets inside of PHI is almost every single large building passive house in Canada is negotiated a project-specific PER. And as a matter of fact, there's already a draft tool that's available for the PHI certifiers that helps define a new PE or PER target that is more amendable to North American densities in multifamily buildings or multi-unit residential buildings. I think everyone knows what these design targets. I'm just looking at the peak design targets to get an idea of equipment sizing. I'm actually using them to size equipment in some of these slides. It's not exactly the number your designer is going to get when they do the math, but it's order of magnitude kind of close. And of course, what we're trying to do is, go from these giant pieces of equipment to, smaller pieces of equipment, something like that. What I'm showing here in the top here is these are my traditional buildings. I've seen how much space heating we typically see in them, the projects I've been involved in the past. Some of them have been quite good, getting down to 32 watts a square meter. But of course, our passive house targets are in the 10 to 16 watts a square meter for a passive house. Space cooling, we've gotten projects in the industry that are 800 square foot per ton. That works out to 47 watts a square meter. Of course, if you're looking at FIAS, we're trying to get down to 11 watts a square meter. So, these are some of the best buildings I've been involved in, and passive house is still asking more out of them. So what's the job? This is coincidentally not that much different than the condo suite I just bought and moved into. But what do we have to do? We have to provide ventilation to all of the spaces. We need to provide exhaust extraction to the kitchen, of course, and the bathroom. Maybe the washer dryer. I just put a ventless heat pump dryer in. It works wonderfully. Got rid of the bulkhead. The builder was like, would you know about heat pump dryers? So that can be certainly dealt with. Of course, we need to provide heating, typically at the perimeter. That's where the heat loss is, or at least in those perimeter spaces. And we need to provide cooling everywhere, and at least dehumidification, especially here in Southern Ontario. So that creates some challenges. And so what's been happening in the normal industry, those that aren't looking at passive house, is one, you'd be surprised, there are actually, I would say, roughly 50% of condo developers and large multifamily building developers are now doing heat recovery. Mostly, I asked them to do it for air quality reasons, to get, deal with stack effect issues and so on. They're mostly doing it because the building code is making them do it because they insist on using window wall. So you do a bad thing, you have to do a good thing to balance it out. So there's an awful lot of heat recovery ventilators going in. And then by far the most common mechanical system is this, the vertical fan coil. And what's lovely about the vertical fan coil is it comes complete with the plumbing. You don't hire a plumber separate from the guy that's installing the fan coil. It's the same damn thing because it just goes into the building, chunk, 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 and that is the plumbing riser. This is a huge capital cost savings for someone building one of these buildings. And of course, what's the smallest one of these things you can buy? Roughly 300 CFM, and we need like 90 to meet our loads. They also end up generating bulkheads everywhere, so this is where the fan coil unit would be, often coupled with an ERV. It could be an integrated ERV or a separate ERV. I would prefer you use a separate ERV, an integrated ERV, almost impossible to balance in one of these things. You end up with bulkheads all over the place to distribute cooling air into the interior. Our exhaust is coming back from the bathroom, has to be exhausted outside. Our fresh air intake, the kitchen exhaust typically going directly outside. So yeah, we end up with bulkheads everywhere, but we save a lot of space. It's a very tiny footprint. It's usually just in the corner somewhere. You know, again, this is what everyone defaulted on because of the plumbing savings. There's lots of the people making them, but as I said, the smallest one I can find is 300 CFM. That means we're delivering 2.5 to 11 kilowatts, 2.5 kilowatts at CFM, at 300 CFM, when, you know, we need, no, it's one of these would do 4 suites designed to passive house. So there you go. But you can buy a smaller boiler, of course, when you combine this with a hot water system. Ventilation, what's been happening with passive house projects is most likely, especially in PHI, because of that exterior duct is treated as part of the enclosure, is on both the supply and exhaust side. Instead of going through an ERV in every suite, the pressure has been to put one ERV on the roof, spider it down, put in the ductwork. And that's what been mostly doing in most of our large passive houses. I have issues with that design, mostly because with people open a window in the cold weather, the stack effect immediately unbalances the system. So it was balanced on the day you balanced it, but as soon as people start using it, it's no longer balanced. So I would much rather, so you can get an idea how it would work inside the suite. You could spider it down. This would serve this in the suite next to it. Put an ERV, sorry, that is the ductwork, the ERV is on the roof, exhaust from the kitchen, supply to a couple spaces, air pattern through the space. I would much rather see a per floor ERV or every 2 floors ERV. This now gets rid of the stack effect issue. It does still minimizes the amount of outside air ducts that are through part of our heat loss. It means you got to find some space architecturally, and also means that you're, we actually have an old project that was done for Lee that did this in Regent Park. Because the distribution is often in the corridor, that ceiling starts getting a little low. And when it's a 200-foot long corridor that's only at 7'10", it starts feeling a little cave-like. So that is one of the challenges of doing that distribution, but there it is. And now, of course, the distribution of suite kind of similar, except we can now tie it to the corridor. Now, moving on to heating and cooling. I think most people know this, but if you ever want to see it graphically and visually, if you want to move heat and cool around the building, you can do it with air, you can do it with water, and these days you now can do it with phase change materials we call refrigerants. This is roughly the math of how much energy it takes to move 1 kilowatt of heat or cooling, but I like to show it in bar graphs. Moving hot air around is expensive. Moving hot water around is a lot easier, and moving hot and cold refrigerant doesn't cost anything. So that's kind of why we like to heat and cool with water instead of air, and then we have local fan coils here. And also that translates into the size of your pipe. How big is the pipe you need or the duct you need to move this heating and cooling around the building? The duct, the pipe, and the refrigerant is the tiny little point down there. Now the refrigerant line still needs insulation around it, so it ends up being about the same size as the pipe in the end. And the other thing, of course, everyone's aware of is I've been amazed how fast the market's conversation has moved from energy to carbon. Carbon has become the new watchword, and now I'm wondering how much insulation we can afford anymore. And I'm starting to see all these embodied carbon numbers, and they're starting to show. I just finished the net zero building 2 years ago. It's minus 17 kilograms we're a carbon sink per square meter in carbon. Our embodied carbon, that already emitted carbon, was 500 kilograms a square meter. So we have a 27-year payback. We're going to pay it back. Most buildings don't pay it back. But we do have a very good big trend to electrification because of our clean grid here in Ontario. You can see our clean grid provinces, which happen to be where most of the population is anyway. So in Canada, like about 70% of the population lives in a low carbon grid. So this is definitely pushing people to consider heat pumps. I will get a hallelujah here. We are starting to see cold climate air to water heat pumps arrive. They're just starting. So they're both from the Maritimes. I don't know what's going on in the Maritimes. One is in New Brunswick and the other one is Nova Scotia. They're good for about 30 kilowatts. So if you're thinking of a MURB, a small MURB, you could probably do like maybe 4 or 5 of these to do 50, 100 suites or something. They can do useful heat down to -30. They only produce 40 degrees Celsius. You're not going to use them to completely heat your domestic hot water, but they're compatible with all your domestic systems. They work the same way as cold climate VRF. It's a two-stage compressor. And so that's a nice option that's coming up. In-suite options. So most of the market is into those vertical fan coils. We can't find them small enough. I did find a horizontal fan coil, only one, after several hours of Google searching, down to 90 CFM. This is actually size to heat and cool a passive house suite around 750, 800 square feet. You'll need a little more larger bulkhead where you install this, which means you might be considering moving it to, say, on the roof of the bathroom, in the roof of the washer-dryer closet, or someplace that already has a drop ceiling. So you don't have as large a bulkhead in the living space, but you can do that. So here's an idea of what it would look like. The black would here would be the fan coil. There's my ventilation. We introduce the ventilation after the fan coil, so I don't have to run the fan coil to deliver ventilation in the space, right? And save some energy, turn the fan off when it's not needed. And we can distribute that heating and cooling throughout the space and something that looks like that. There are non-ducted fan coils. They don't look that much different from the old window shakers that in your hotel room. They run off hot and cold water. So again, sorry, backing up, there's a hot water distribution riser there, hot and cold water. But most of them are still pretty large. They tend to be still 2 and 3 times bigger than we need. You could install them like this, but then the problem is, if I have an interior space, I have to then plumb water over there. You're probably going to do that plumbing in the suite below through their drop ceiling, and you also, if you're going to do cooling, you're going to need a condensate drain. So, this becomes a little challenge, and this is why a lot of people end up doing air for heating and cooling just in the suite to avoid all this extra plumbing and condensate. Cooling climates have extra challenges. We have baseboard convectors. The nice thing about baseboard convectors is they're kind of available in any length you want. So it's pretty easy to size them for heating. There are some numbers here of what kind of load you would want to kind of meet a 600 to 1,000 watt peak design load in a passive house suite in one of these buildings. So that's kind of nice. And at these temperatures here, they're heat pump compatible, low temperature. But here's the problem, of course, you can provide heating but not cooling, so now you got to find another way to cool the space. So we have done work and studies that says if you're really good at doing your passive control, if you dehumidify the air, you may only experience temperatures of high as 25, 26 Celsius. So they'll be slightly warm, but at least they'll be dry for dehumidifying the air centrally at your HRV. I like these, and actually one of the big developers is using these, Tridel now. These are essentially fan coil convectors. They're baseboard radiators that have little fans on them, highly efficient fans. The fans don't even turn on unless they're needed to the extra boost for heating and cooling. They can do heating and cooling. They're called Jaga. Then there's some of the sizing that you would need and how long you would need it, but to deliver this much heating and cooling. They're available in a trench. They're available in a more conventional looking radiator, but they're a pretty interesting option. This is how the trench would work, and they have, like I said, they mentioned a little fan in there. And how you would also distribute it, but again, you have that same problem. If you want to cool that off that inside space, you got to find a way to put plumbing in there from your main riser, or put another riser in the building. Radiant heating and cooling, actually this is happening in a project in Guelph that's targeting net zero and net carbon zero performance. They're doing radiant cooling. This example here is radiant heating. This is how much heat you get out of a floor for whatever temperature the surface is. So just a little thermoanalysis for a 23-degree floor. So if you want 21 degrees, you're here. You're already at 20 watts a square meter. Now, that's more than you need, but you don't get all the floor space because people like to put furniture on the floor, and radiant heating systems only heat what they see. So you got to derate that somewhat, and we're only providing 24, 25-degree water to these pipes. You can do that with solar thermal. Put some solar thermal on the roof. Radiant cooling, kind of the same idea. Again, this is the type of output you get of a radiant surface, whether it's the floor or a ceiling. Tends to be closer to the same with cooling. And, excuse me, kind of a range we'd be targeting for passive hosts in around here. But if you push that delta, now you're talking a floor that's getting close to 15 Celsius. One, it's super uncomfortable, and two, you're at risk of creating slippery stuff. The challenge, of course, with radiant cooling is you need to dehumidify. Now, if you're doing passive host with a central HRV or one per floor, you probably have a cooling coil there. You're dealing with the humidity there. This particular project was doing HRVs per suite, which meant we now had to find a 100 CFM dehumidifier coil, which is really, really hard to find. But it turns out Honeywell does make one. Unfortunately, this is the old-fashioned dehumidifier that the heat literally goes back into the space. It's capable of removing 65 pints of water today, which is, 8 times more than we need. But it's the smallest one we can find in the market. And then now moving into VRF. So this is now we have refrigerant lines throughout the building. We're doing all our heating with heat pumps. Could be a water-cooled heat pump connected to a Geo-exchange system. Could be a water-cooled heat pump connected to a boiler and a cooling tower. Could be an air-cooled heat pump, air source heat pump. The big limitation here is how small can you buy the cassettes, whether it's a wall-mounted cassette or one that's a vertical fan coil or a horizontal fan coil in the ceiling. Smallest ones I can find bottom out at 1,800 watts cooling, 2,000 watts heating. Again, they're almost 2 to 3 times the size we need per suite. And one of the challenges with VRF is you can't necessarily buy the smaller central heat pump that just matches your load. So here's an example, a building with a total design load of 10,000 watts, but because we had to buy these larger units, we've installed 30,000 watts of these things, but the heat pump I had to buy, the central heat pump, isn't 10,000, it's probably some number in between, it's like 20,000. So that's one of the challenges with VRF. Of course, the other challenge with VRF and how you would locate it in the building, kind of the same thing as the other fan coils. With the water-cooled ones, you can install the water-cooled heat pumps, 1 on every floor or 2 or 3 on every floor, depending on the size of the load. Again, you need a vertical distribution riser. With the air-cooled heat pumps, you pretty much can only go about 40 meters vertically. So as your building gets taller, you have to, and not only that, but you start losing COP. So I would recommend trying to keep it around 20 meters vertical. So most of the passive host buildings that have gone this way are putting basically mechanical balconies on every floor. They got to put a doorway in there so they can do maintenance. But basically the VRF air source heat pumps are going outside, which is of course what Cornell did. Okay, domestic hot water. We need 60 degrees Celsius, to kill Legionella, we need 60 degrees Celsius for 32 minutes. That's what kills it. Most of our air source heat pumps and water source heat pumps don't do 60 degrees Celsius, they do 40 degrees Celsius. Which means we're either preheating and then doing the rest with electricity, which means our standby losses are all electricity, which means it's actually a lot more electric resistance than you think it is. But hallelujah, we do have some solutions. If you have ground source heat pumps, we now have these templifiers that can actually deliver you 60 to 70 degree heat off of a ground source, or they can also capture heat off of maybe the drain water. They can capture heat off of sewers or any other waste heat source, so they can work. But what's on the horizon, and really there's only one on the market that's being targeted for residential, but other people are jumping in. As I mentioned, Lars is jumping in. This is Mitsubishi's. This is a new one I just found out the other day. These are all supercritical CO2 heat pumps. They produce 90 degrees Celsius water when it's minus 30 outside. They are at insane pressures on the inside. Your normal refrigerant guy is not going to work on this because they're running at about the same pressure as a diesel engine fuel injection system. That said, more and more of these seem to be showing up. Right now, they're all in that 30 kilowatt capacity, and with the exception of Sandon, the rest of them are marketing to industrial right now. So you can go to Mitsubishi and it's in their industrial department. They don't understand why you'd want to use it in a residential building. But they do sell them. Okay, conclusions. Yeah, we're really still challenged to find right-sized equipment. I would love to see the 90 CFM vertical fan coils that eliminates the pumping and moving to an air-to-water heat pump. I think that'd be an awesome solution. We're getting more options for cold climate air-to-water heat pumps. They're slowly becoming more available, which means we can go to all water systems. I don't hate VRF, but I don't know what I'm going to replace it with in 20 years. And I lived in a VRF building, we had a leak, and then we did the math, and that was 1.5 years of our carbon savings from the energy efficient design disappearing in one leak. GHG emissions, pressure is going to keep increasing. We're going to see more heat pumps. I'm going to do this speech to Enbridge next month. I'll see how that goes. I said these new sets are 7444. I'm really interested in what's going on that, mostly also for the retrofit market. This is a drop-in replacement for boilers, is what these heat pumps are, especially when they get available at larger sizes. And cooling climates, I wish we had Vancouver's climate because they don't even think about cooling, although every time we do a future study on our passive host projects out there, we tell them, and by 2050, all your passive host projects without cooling are going to be overheating. Welcome to climate change. That's all I have. Thanks.